Okay, good day, students. Welcome back to DBMS course, and now we are in chapter 5, part 2. And in this sections, we will look into normalizations and denormalizations. Okay, let's start with normalizations in these chapters, and then we will go into some various normal forms, includes one normal forms, and then second normal forms, third, and then B, C, and F. It's a boys normal form, then four normal form, and the fifth normal form. And after that, we will look into what is called denormalization. Okay, we'll start with normalization first. So we have discussed normalization definition in the previous sections in chapter 5, but in this chapter we will go into detail into normalizations. So normalizations is basically how we understand some various anomalies or pitfall in a relational database. Okay, to start out with the normalization, we go into the definition first. So definitions of the normalization is a process, a systematic process in database designed used to break down, or we can say to decompose a large tables into smaller, and we make it more organized, and to eliminate what is called anomalies. The anomalies here is the problems like the redundancy and inconsistencies in a relational database. So by organizing data more efficiently, the normalizations will help to ensure that the database is easy to manage and easy to update and easy to query. All right, there are some steps of normalizations, which is called normal forms. So normalizations is done in some steps where each step is called normal forms, or we can uh, abbreviate to NF. So each normal form has some specific rules that the database needs to satisfy to achieve that form. By moving through these normal forms like first an F, two and F, three and F, and etc., a database becomes more structured by reducing data duplications and errors at any stage. Okay, so we have some steps. Yeah, the first is a first normal form. So the first normal form will ensure that each column will contain only atomic values or indivisible values with no repeating groups. And then for the second normal form, so we build on the first normal forms by ensuring that all non-key attributes are fully dependent on the primary key by reducing the redundancy. And then for the third normal form, it will ensure that the non-key attributes are not dependent on the other non-key attributes, further minimizing the redundancy and the anomalies. Each step of this addresses specific kinds of redundancy and inconsistency issues, making the data structures progressively better and better. So, normalization is more like a reversible process. This means that if you've broken down a table into smaller tables, or relations during normalizations, you can combine them back into a larger table if needed. And this ability to reverse the process is useful when performing certain database operations or when revisiting the database design. So, in summary, normalization is more like a structured process of decomposing tables step by step into smaller, organized tables to remove the anomalies and to achieve a better and more logical structures. The step by step nature or normal forms and the ability to reverse the process makes the normalization a flexible and essential technique in database design. Alright, so the purpose of the database design is to arrange data without repetition. By organizing data carefully, the database design will be able to minimize the data repetitions. This reduces storage cost and will ensure that when data is updated in one place, it doesn't need to be replaced or it doesn't need to be updated in multiple places. And generate structure relationship. Okay, so database design establish structured relationship between different tables using keys like primary keys and foreign keys. And this relationship make sure that the database reflects real-world connections and that each table can be linked logically to the others. Talking about the benefits of the normalizations, of course, it will reduce the redundant data. So, normalizations breaks down tables into smaller ones that each focus on a specific entity, which reduces or eliminates repeated data across the database. And it also ensures the data inconsistency with reduced redundancy. The normalizations ensures that each piece of data is stored in only one place. So when it's updated, there is no need to worry about inconsistency. For example, if a customer's address changes, you only need to update it in one table rather than several tables, something like that. So overall, the normalizations will help to create a well organized and efficient database that's easy to maintain, reliable, and optimized for data integrity. So again, the normalization is a process in database design with the goal of organizing data efficiently by structuring tables to reduce redundancy and prevent anomalies. Okay, so definitions of normalizations is includes deciding attributes grouping in relations. In normalizations, you decide how to group attributes in columns, in tables, or relations based on their logical connections. This means carefully selecting which attributes should be grouped together in the same table to ensure that the data is organized logically. And it's also decomposing relations with anomalies into smaller and organized relations. If a table has a problem like redundancy or anomalies, for example, insert, delete, or update anomalies, the normalization involves decomposing it or breaking it down into smaller tables And these smaller tables are organized so that each one holds a specific set of related data. And then they connect to each other through keys, such as primary keys or foreign keys. So, the outcome of this normalization is a set of well organized tables without redundancy. Okay, so each piece of the information is stored is only once, which reduces unnecessary duplication. And of course, it will prevent anomalies. With a clear structure, the database avoids update, insert, and delete anomalies, making it easier to maintain the consistency. Through the normalizations, a database is transformed into a structured, efficient design that minimizes the redundancy and ensures the data integrity. Okay, so let's talk about the benefits of normalizations. So the benefits of the normalizations includes smaller tables. Normalizations create smaller table where the smaller rows mean more rows per page and less logical input and output is needed. And then it's improved performance. Searching, sorting, and creating indexes are faster. The lower tables mean more rows fit on a data page, something like that. And more tables, we need to split original tables result in more tables, right? So more clustered index provide flexibility in turning the queries. It's also faster index searching. The index are narrower and shorter, so it will make the search more quick than before. It's also better data placement. More tables allows you to have a better control of data placement using segmentation. Okay. It's also faster data modification. Yeah. So fewer indexes per table will speed up data modifications command. It also less reduce the anomalies. Yeah, it's fewer data modification anomalies. It's also easier to maintain. Yeah, conceptually cleaner and easier to maintain, easier to change as needed to change. Okay. All right. Now we are moving to the next sections explaining about the various normal forms. Okay, we'll start with the first normal form over here. First normal form of 1 and F in database normalizations. So, first normal forms is a relation or table. In a first normal form, if each attribute or columns contains only atomic or indivisible values, automaticity is required for a relation to be first normal form. Okay, so consider an employee relation table with a name attribute that combine first and last names. Okay, first and last names. This name attribute is not atomic because it contains multiple pieces of information. So to achieve first and F, we need to split the name attribute into two separate attributes. Okay, so we have a first name attributes and second name attributes. This ensures that each attribute contains only atomic values. So, as we can see in this slide, the left table is the table where it's before the normalizations, and the right one is after the normalizations where we have two attributes for name. So by splitting that name attribute into first name and second name, the table now satisfies the requirements of the first normal form. All right. So let's move to the second normal form, or 2NF. So the definition of the second normal form is something like this. Okay. So in a relation in a second normal form, if it is in first normal form and all non-primary key attributes are fully functionally dependent on the primary key. All right, let's move to the example for your better understanding. Consider a student relation with attributes like roll number and then the game, name, fee, and grade. The primary key is a composite key, means the roll number and game in this case. Okay? So the problem in first number form, the student relation in first number form still has anomaly. Sorry, first normal form, because still have anomalies if it has a deletion anomalies. Deleting a student in this table might remove information about Kim, right? Okay, and for example, if we want to add a new game without any students cannot be done. So it's also considered as a insert anomalies. And when we change the fee of a game, it will require updating multiple records to inconsistency, which is leading to inconsistency. So we need to separate the partial dependency from the fully functional dependency. Okay. So in this table, we need to split the original relation into three new relations. Okay, so the first we have a student with roll numbers and name. Okay, and then the second tables contain game and fee, and performance. Okay, performance includes roll number, game, and grade. So in this case, we have some benefits. Yeah, it eliminates some anomalies. We eliminate delete anomalies. So removing a student does not affect the game informations, right? And then if we have a new game, the game will be uh, able to edit without needing students in this case. And if we change the game fee, changing the game fee is done in one place. Okay, so no need to update all. It's to maintaining the consistency. And by splitting the original tables into one, two, three tables, the each tables now conforms to the second normal forms and avoids the anomalies mentioned before. Alright, that was second normal form, 2 and F. Now the third normal form, or 3 and F. So a table or relation is in third normal form if the table is already in second normal form, which means there are no partial dependencies where non-primary key attributes depend on only part of a composite primary key. Also, there are no transitive dependencies among the non-primary key attributes. A transitive dependency is when a non-primary key attribute depends on another non-primary key attribute rather than directly on the primary key. This can cause the data inconsistencies and redundancies. Alright, for examples, we have a students table over here. Let's say we have a student table with the following columns. The roll numbers is the primary key, and the name, semesters, and hostels. Okay, so each student has unique roll numbers, and they are assigned different hostels for each semester. Okay. So there are issues in 2 and F, the second normal form. The student table is in second normal form because all the attributes depend on the primary key, in this case roll number. However, it has some problem. It still has some problems called anomalies. So the anomalies consist of three anomalies. The first one is delete anomalies. If we delete a student, we might also lose the important information about the hostels. For example, if Gaurav is the only student in hostel H2, and then we delete this record, the information about hostel H2 is also lost. Okay, so it's called the delete anomaly. And then the second anomaly is called insert anomaly. If a new hostels H8, for example, is added into the tables but has no students yet, we cannot store this hostel in the table since there's no student record to attach it to. So that was called insert anomaly. And the third anomaly is called update anomaly. If we want to move all first semester students to a new hostels, we would have to update its record one by one. This is completely inefficient and error prone, as some records could be missed and leading to inconsistency. So the solution we need to divide it into third normal form, and we divide the student table into two tables. Okay, the student with roll number, name, and semester. This table stores student information without the hostels details. And then we have hostels table with the semester and hostels detail. So the table stores hostels assignments for each semester. Okay, so now each piece of information is stored in the correct table. So if you want to make any updates, if you want to make any insert or delete, it's more straightforward and consistent. All right, is the next normal form is called Beyond's no, it's boys called normal form. It's not Beyonce, okay? Sorry. Everyone's talking about Beyonce nowadays. Okay, forget it. Okay, so B, C, and F is the structure form of third number form, right? It's the advanced version of third number form, and it's strict, more strict, related to its requirements. So for a relation or table to be in the B, C, and F, first it must be in a third normal form. Okay, and then every determinant in the table must be a candidate key. And determinant is an attribute or set of attributes that determines another attribute. So in B, C, and F, all the attributes that can determine other attributes must uniquely identify rows. It means that they must be a candidate keys. Okay. So BCNF is particularly useful when a table has multiple candidate keys, which can cause anomalies in tree and F structure. Okay, so we go into the examples for your better understanding. Consider student relation with attributes of roll number, subject, and teacher. Okay, so each student can have more than one subject. Okay, and each teacher teaches only one subject in this case. A subject can be taught by more than one teacher. Okay, so in this table there are two candidate keys. Okay, can you guess? The roll number and subject, and then roll number and teacher. So these two are the candidate keys. It means that we can actually uniquely identify each records by either use the roll number subject or use the roll numbers and teachers. However, even though the table is in third normal form already, it still has the anomalies because of the overlapping candidate key. So what do we do? First, we need to realize there are some problems in third and F. Okay, there are some anomalies in the third number form student table. All right, there are three anomalies in this case. Yeah, we have delete anomalies, insert anomalies, and update anomalies. So the delete anomalies, if we delete a student with roll number, for example, roll number 7, so we might also accidentally lose the information that teacher T4 teaches the subject Phoebe if there are no other records linking them. Okay, that was the delete anomalies. And then we have also anomaly called insert anomaly. If a new subject of phi C++, for example, is introduced, we cannot add it to the table until a student enrolls in it and the teachers is assigned to it. Okay? And then the last anomaly is the update anomaly. If we need to change the teacher for subject C, for example, we must update each record where subject C is assigned, which is, I believe this is inefficient and can lead to inconsistent data if any records are missed. So the issue is over here is about the overloaded candidate keys. As you can see here, so in this table, the roll number is overloaded, meaning that the part of the bold candidate keys and connects multiple pieces of information. So we can find teacher by using roll numbers and subject. We can find the subject by using roll numbers and teacher. We can find a subject by using teachers only. So this overload complicates the table structure, which leading to the anomalies is which is described before. So that we have a solution, we need to decompose into BCNF, okay? To achieve BCNF, we need to split the student table to ensure that all determinants are candidate keys. This results in two separate tables. Student teachers, which consists of roll numbers and teacher. This table links students with the teachers, and we have another table called teach sub. So it's between teacher and subject. So these tables links the teacher with the subjects they teach. Now, this table, the student and teacher, lets us know which teacher is assigned to each student, right? And this sub lets us know which subject each teacher is qualified to teach. And in this structure, all determinant like roll numbers and teachers in teach, teacher and subject in teach sub are the candidate key. So each table is in BCNF, eliminating the anomalies. So in summary, BCNF eliminates the remaining anomalies found in a third normal forms by ensuring that every determinant is a candidate key. This approach is especially useful when the tables have many candidate keys, as it will organize data more clearly and ensures the efficiency and consistent updates. Okay. Now, the next normal form is called MVD. It's the multi-value dependency. And the fourth normal form. Okay, so I will explain these two separately, but it's still connected to each other between MVD and fourth normal form. Okay, in this slide, I'll explain to you about MVD. So, multi-value dependency or MVD represents a type of dependency in the database where the two sets of attributes are related but independent of each other with respect to a third attribute. This can help us to structure data in a way that avoids unnecessary duplication and anomalies in databases. Okay, definition of an MVD. Okay, given a relation of R with the attributes of A, B, C, where the B is multi-dependent on A, if for a given value of A, the set of B values is independent of the C values. So, in other words, knowing that A allows us to determine B values regardless of what the C values are. For example, if we have a percent of A with multiple phone numbers of B and multiple addresses of C, the phone number associated with that person don't depend on the addresses, right? So the person's name is multi-determining their phone numbers and their addresses separately. Okay? Okay, talking about the MVD rule. In if a relation of R with the attributes of A, B, and C has an MVD, MVD means uh this symbol, so double right arrow. Then we also have A determines C as well. Okay. This means that if A determines a set of B values independently, it also determines a set of C values independently. All right. Another way to understand the MVDs is by considering tuples in a relation. If a relation of R has an MVD A to B, then if we have two tuples of T1 and T2 with the same value of A, then there must exist two other tuples, right? The T3 and T4 that also share the same A values as T1 and T2. T3 and T3 has the same B values as T1 and T4 has the same B values as T2 for the attributes not in B, yeah, referred to as a RB in T2 and T3 should share the same values. And T1 and T4 should also have share the same values for R and B. This means that the B values can pair with any of the C values independently within the same A values. All right, now the trivial MVD. So and MVD of A determines B is trivial if B is a subset of A or the union of A and B includes all the attributes of R. This means the MVD does not add new information or dependency rules. If B is part of A or if they together cover all the attributes in R. Okay? Now I'll explain the fourth normal form. The fourth normal form is an advanced level of database normalization aimed at handling the multi-valued dependency, the previous one, MVDs. A relation reaches 4 and F when it meets the requirements of B, C, and F, the Boy's code normal forms, and additionally has no non-trivial MVDs. So a relation is in a fourth normal form if it is already in BCNF and it contains no non-trivial multivariate dependencies. This means that if there is an MVD, it should either be trivial or have a superkey on the left side. Okay, so a relation is in fourth normal form if it satisfies the BC and F first, and for any multivariate dependency of X and Y is trivial. It means that Y, a subset of X, or X and Y together cover all the attributes. So in this case, the X is the superkey of the relation. Alright, now let's move to the examples and solutions. Let's look at a sample relation of project work with the following attributes. We have a programmers, we have project, and we have module. Assume that a programmer can work on multiple projects and each project can contain multiple modules. Okay? So given the assumptions, the following multivariate dependencies exist. Programmers can work on many projects independently of the modules, and a project can have many modules independently of which programmer is working on it. Okay? Okay, so in BCNF, there are still have some anomalies So in BCNF, we sometimes still face what is called data anomalies because of the multi-value dependencies when the multiple candidate keys exist. So these anomalies are includes the following: the delete anomalies, insert anomalies, and update anomalies. So for the delete anomalies, if we delete a project, we might lose information about programmers associated with that project, right? And then if we want to add new project, we cannot add a new project until it has a programmer assigned to it, which restricts adding project independently. Okay, and then update anomaly. If we change a project's name, we need to update all the records where this project is listed. It increases the risk of inconsistency for sure. So what's the solution? Okay, to avoid this kind of issues, we can further split the relation to better isolate the independent information. It means that we reach the fourth normal form. Okay, so we have new two relations between the programmer and project and project and module. This relation, the first relation, tracks which programmers are assigned to which project. For the second relations, these relations keep tracks of the modules belonging to each project. Okay? By splitting the original relation into these two, each table independently handles its dependencies. Okay? And the program and projects allows us to manage programmers and project associated without worrying about a module, right? And then the project module allows us to manage project and module relationship without requiring programmer information, right? So this approach will eliminate the redundancy and preserve the information integrity so that we can solve the delete, insert, and update anomalies that can still occur in the BCNF. All right, the last normal form for normalization is a projection join normal form, or we can also call it fifth normal form, and a join dependency. Okay, before we go into the fifth normal form, I would like to explain the join dependency first. A join dependency occurs when a relation of R can be decomposed into smaller subrelations of R1, R2, R3 until Rn. And when join them back together, they reconstruct the original relation, where this means that no data is lost or duplicated in the process, and the structure of the original relation is preserved. In other words, if you split a relation into smaller parts, they should be able to join back together perfectly to form our original relation. Okay, so we have an examples over here, examples of join dependency. Consider a relation of x, y, and z with the attributes of x is the customer ID, represents the customer ID, and y represents the account ID, and z represents the branch ID. To ensure that each piece of information is stored independently without redundancy, we might split the XYZ into three separate relations. Okay, we have three separate relations over here. We have XY. It contains pairs of customers ID and account ID over here. And then we also have YZ. It contains pairs of account ID and branch ID. And next we have ZX. It contains pairs of branch ID and customers ID. If these three relations, 1, 2, 3, satisfy the join dependency, then we should be able to join them back together to reconstruct the original XYZ relation accurately, containing all original information without any loss or anomaly. All right, the projection join normal form, or we call it fifth normal form. The definitions of the fifth normal form: a relation of R is in fifth normal form if it is in fourth normal form and every joint dependency in R is trivial. Okay, so in simple terms, that means that a relation in fifth normal form can be decomposed into small parts without losing any information, and that those parts can always be joined back together to perfectly reconstruct the original relations. This ensures that there are no hidden dependency that could cause the anomalies even with complex multi-attributes relationship. Okay, there are some key concepts about the fifth normal form. So we have a trivial joint dependency. A joint dependency is trivial if the composition of relation does not lose any information and can always be perfectly reconstructed by joining the decomposed relations. So there are some properties in fifth normal forms. So in fifth normal forms, a relation cannot be decomposed further without potentially losing information. So we have some anomalies in fourth and F relations can occur when there are complex dependency involving three or more attributes in the primary key. So the fifth normal form here aims to eliminate these issues by further decomposing such relations. So talking about the pairwise cyclical dependency. So in some relations, knowing two values is quite necessary to determine a third. This is called cyclical dependency, where each attribute depends on a pair of others. Okay, let's check the examples. We have a buying table, the original relations of buy table. Okay, we have the attributes of buyer, item, and vendor. So the buyer here, uh, there is a problem in this table. Can you find the problem? Or can you find the anomaly? If a new vendor, let's say HCL, starts selling computer, the multiple records would need to be recreated for each buyer who could buy from HCL. This will lead to redundancy and update anomalies as each combination of buyer items and vendors need to be listed separately. So, as the solutions, we need to eliminate these anomalies so we can decompose the buying table into three separate tables. This decomposition preserves data integrity and allows us to reconstruct the original table by joining this smaller table. Alright, we have a buyer vendor table as the first separate table. It consists, this table is capturing the relationship between buyers and vendors. Okay, and then we also have buyer item table. This table captures the relationship between buyers and items. And the third one is the vendor item table. This table captures the relationship between vendors and items. Alright, as the conclusion, each of the three decomposed tables in a fifth normal form, by splitting the original table in this way, we have ensured that there is no redundancy and that any new vendor or item relationship can be added without needing redundant entries. Additionally, joining these tables can perfectly reconstruct the original buying table without any loss of information. Alright, everyone, now we move to the next section of this chapter. It's called denormalization. Okay, in this section, we will understand what is denormalization. Is it same with the data model that has not been normalized or not? Let's see. What is denormalization? So the normalization is a strategic approach used to optimize the performance of a database by intentionally adding redundant data or grouping data. This process should only be considered after achieving a satisfactory level of normalization and ensuring that any required constraints and rules are in place to handle the inherent anomalies in the design. Okay, again, the definitions of denormalization. So, the normalization is the process of reducing the degree of normalization in the database by reintroducing some data redundancy. Okay, so it's the process of reducing the degree of normalization in a database by reintroducing some data redundancy. This is done specifically to enhance the performance of the query processing. So, what's the purpose? The main purpose of the normalization is to minimize the number of physical tables that must be accessed during the queries. which in turn reduce the number of joins required to retrieve the data. This approach will speed up the data retrieval and making the systems more efficient for read-heavy operations. However, this kind of performance will boost in querying, often comes at the expense of the increased complexity in data modification and potential redundancy issues. All right, the process of denormalization. Okay, in the database design, the normalization involves splitting larger tables into smaller ones, right? It is to reduce the redundancy and to ensure the data integrity. While this approach, the normalization, prevents data anomalies and promotes consistency. The normalization. I'm still talking about the normalization. Okay, so this approach prevents data anomalies and promotes the consistency and often results in a higher number of tables. Consequently, the queries must perform multiple joins across the tables, which can reduce the query performance, especially in large databases with frequent read operations. So that we have a the normalizations over here. So it's the process of intentionally reintroducing some redundancy to improve the performance of the red heavy applications. So it combining related data into fewer tables or by storing the redundant information, the normalization reduces the number of joins required in the queries, which can improve the response time. Okay. The DBMS may also store the redundant copies on a disk specifically for query optimization, but it manages these copies carefully to keep them consistent with the original data. For examples, the indexes, materialized views, or even computed columns might be used to store frequently queried data redundantly, ensuring that query performance improves without sacrificing data accuracy. So, in summary, the normalizations strikes a balance between data integrity and performance. It trades some redundancy for faster data retrieval in scenarios where the read efficiency is critical. Okay, there are some strategies in terms of the normalization. First is the logical design normalized, or we can say physical storage optimization. So in this strategy, the logical designs of the database remains normalized. It is to maintain the data consistency and clarity. However, the physical storage is optimized by allowing the DBMS to store the redundant data specifically for improving query performance. This approach will leverage the indexes, the materialized views, or replication to reduce the query time while keeping the data model simple and consistent. And then we also have the normalized logical designs as a second strategies for the normalization. Here, the logical data design is intentionally adjusted to reduce the number of joins required for frequent queries. This may mean that combining data that would otherwise be normalized, resulting in fewer tables for common queries. So, to maintain the database integrity, the constraints are applied to ensure that even with denormalization, the data remains consistent and reliable. Okay, so what are the goals of the normalization? It's improving the query performance. Okay, by reducing the number of joins and potentially storing pre-computed data, the normalization can make critical queries faster, especially in cases where large datasets are involved. And then it presents a simpler and more user-oriented view of data. The normalization can provide a more intuitive data structure for end users, which can enhance the usability for those interacting with the database regularly. That's why we call it a user-oriented view of data. And the last goal is about reducing the complexity of the database for end users by minimizing the number of tables and joins that required can simplify the database interactions for end users, making data retrieval more straightforward and faster for applications and reports. By implementing these strategies truthfully, the databases can balance the benefits of the normalized design with the performance gains of a denormalized structure tailored to the needs of the users and the application's requirements. The normalizations can be beneficial when certain indicators, such as it might improve the performance or simplify data handling. So the key indicators includes the critical queries and reports relying on data from multiple tables. When important queries require frequent joins across the several tables, the normalizations can improve the performance by reducing the number of joins needed. And then repeating groups that needs group processing. For data structures with repeating groups that must be processed together, the normalizations can simplify queries and speed up the access by consolidating data into a single table. Columns requiring calculations before the queries. So, if certain columns need calculations applied before they are used in the queries, the normalizations can store pre-computed values, which is, of course, it will leading to a speeding up the query processing. And then table access in different ways by different users. When different users group access the same table in the varied ways, the normalizing to create different data layouts can improve the query efficiencies for each user group's access pattern. And the last one is the frequently queried columns. For columns that are queried often, especially when joined with the other tables, Storing related data together in a single table can reduce retrieval time and enhance the performance. So, the normalization in these cases can streamline data access and reduce the complexity, improving the responsiveness of the critical transactions, and of course, simplifying the query structure. There are some issues. When deciding whether to denormalize a table, it's essential to assess both the application's performance needs and the specific data access patterns. So there are some key factors included in this case. First one is critical transactions expected response time. Identify which transactions are most critical and determine the response time required. This helps evaluate if the normalization could speed up high priority queries or not. And then the frequency of transaction execution. For frequently executed transactions, the normalizations may reduce load of simplifying data access, which can improve the overall system performance. Tables or columns used by critical transactions and their access rows. Let's focus on the data most often accessed by important transactions. The normalization, the normalizing these areas could potentially provide significant performance gains. Mix of transaction types. Yeah, select, insert, update, and delete. Okay. Determine the balance between read and write operations. The normalization can optimize the read heavy workloads, but may slow down the write heavy ones due to redundant data updates. And the fifth one uses short order. If the transactions commonly access data in a particular sort order, then normalizing with the pre-sorted data can enhance the efficiency by eliminating sorting operations at query time. Concurrency expectation. Consider the expected number of simultaneous users. If high concurrency is required, the normalization may cause con- conten- contention in writes and should be carefully evaluated. And the next issues to consider is the size of the frequently accessed tables. The large tables that are frequently accessed can benefit from the normalizations by reducing the need for joins. However, it can increase the storage space if data is duplicated. The next issue needs to be considered is process computing summaries. For processed that involve complex aggregations, storing pre-computed summaries can improve performance by eliminating the need to calculate these at runtime. And the last issues need to be considered is about the physical data location. In distributed databases, consider the physical location of data as the normalization can reduce the need for cross location joins. It will enhance the performance in distributed environments. So, by evaluating these factors, it will help the company or it helps you to decide if the potential performance gains after the normalizations outweigh the additional storage and complexity it introduces. Alright, there always be an advantage and disadvantage of something. It includes the normalization. Okay, so the advantage of the normalization, it will minimize the need for joins, improving the performance. By storing related data in the same table, the normalization reduces the needs for complex joins in the queries, and this improves the query performance, especially in read-heavy applications. It also reduces the numbers of foreign keys, enhancing the performance. With the fewer tables and fewer relationships, there are often fewer foreign keys, which can make data retrieval faster and simplify the database structure. It saves storage space and reduces data modification time by minimizing indexes. Okay, the normalization can reduce the need for multiple indexes across the tables, but this not only saves storage space but also speeds up data modification operations as fewer indexes need to be updated. And the next advantages of the normalization is precomputers aggregate values, which is enhance the performance. By storing the computed values like totals or counts directly in the table, the normalization avoids recalculating these values on the fly, leading to faster query responses, especially for reporting purposes. It is also reduced the number of tables, simplifying data retrieval. With the fewer tables to navigate, the data retrieval becomes simpler, of course. This structure is easier to work with for developers and can make querying data more straightforward for users. Alright, now the disadvantages of the normalization. Okay, it speeds up retrieval but can slow down the data modification. Yeah, the normalization can improve the speed of data retrieval since fewer joins are needed. However, updates, inserts, and deletes become more complex and time consuming because the redundant data needs to be modified in multiple places. The application is specific and needs re-evaluation if the application changes. Mhm. The normalization is often tailored to specific application needs. If the application requirement change, the normalization, uh, the the normalized structure might no longer be efficient or suitable because it requires further adjustment to the database. And it increases the size of tables, of course. By duplicate the data to avoid joins, the normalization increases the overall size of tables. This can lead to larger storage requirements and a potentially slower performance when dealing with a massive database or data sets. Sorry. It also simplifies coding in some cases, but can make it more complex in others. Yeah. While the normalization can simplify certain queries by reducing joins, it can complicate coding for data modifications. Maintaining data consistency becomes more challenging since updates must be carefully handled to avoid inconsistencies in this case across the redundant data fields. So this is the disadvantages of denormalizations, and of course the advantages. Okay, um, that's all of the chapter 5 sections 2. If you have any questions, just send me email, and I will see you on December to to a presentation of your project. Okay, have a good day. Bye bye.